Welcome everyone. Let me move this out of the way a little bit here. Is everyone aware of what we have been doing?
No.
A lot of people say no.
Oh, okay. So what we have been doing this summer this year is collecting data available from TCEQ at various monitoring sites, which I'll show in one of the next slides. But most prominently, we analyzed in detail the Floresville monitor data. So I'm going to give you a quick overview of not all, but a lot of the results we have obtained so far from analyzing just regular monitor data that are available from TCEQ, either directly online or through requesting them from TCEQ, such as the Floresville monitor data, because it's you can download them online as well, but it's the format that they provide is very cumbersome and typically only good for individual compounds if you're interested. So I will give a quick introduction of what we're dealing with here in this shale and in many other shales. I will go into some long-term changes going back to 2007, and I'll also go over a few case studies and have one conclusion slide in the end. So let's get started on this. First of all, what we are dealing with is what's called fugitives, mostly unburned hydrocarbons, and they represent actually a major source of pollutant exposure, especially for workers. Numerous deaths have occurred at unconventional oil and gas sites because workers were ill-advised or ill-trained in approaching tanks in specific. What you can see here is a typical view of the tank in the visible on the left and in the infrared on the right, and you can see the large amounts of emissions. So this is typically done with these FLIR cameras that are now widely used to look for fugitive emissions from the oil and gas industry. They were very successfully used in Houston after the first Texas air quality study about 15 years ago, almost 15 years ago, when it was found that a large problem in Houston was the enormous amount of fugitive emissions from tanks. So they have addressed that to a large extent, and so the industry, I think, knows pretty well how to minimize these emissions if they want to. Mostly what we get is, of course, the volatiles. So the more volatile a compound is, the more likely it is to come out of these tanks wherever there is an opportunity. Don't forget that these tanks have to have a leak on by default for safety reasons. As they are filled, there needs to be a leak somewhere on the tank to push out the excess volume of gas. So you will not have these tanks to become an absolute zero source. There will always be a source, but it can be minimized. This is probably also the largest source of VTEX compounds, which are of special consideration for public health. Now, it turns out that with the new oil and gas developments throughout the nation, this is a very leaky business, and I'll call it a leaky industry here. Throughout shale areas, there is now a large and growing body of literature showing that these hydrocarbon emissions are enormous compared to what we are used to as scientists when we investigate this type of air pollution. You can go to very polluted cities in the past that used to be Houston. Currently, that is cities in India and China, and you find high hydrocarbon mixing ratios, but none of those rival the amount measured, for example, in the Uinta Basin, where concentrations are at times in the hundreds to thousands of ppb. So very, very high hydrocarbon pollution. So this is very well documented for Utah and for Colorado. There's also some papers coming out for the Marcellus Shale out of Pennsylvania. And I'd like just to give you two examples from recent papers. So this is from the Thompson et al. Paper that just came out about a month ago. Enhancement factors for the C2 to C5 alkanes in 3 different locations: Denver, Erie, Longman, and Platteville. So what you see in these numbers here is the left column, year average background. So those are typical mixing ratios you observe in relatively clean air, typical rural air. Next column is just specific for a particular period. And then look at the Denver and the other places. Platteville, which is essentially surrounded by oil and gas exploration, shows very high mixing ratios, of order factor 100, if not 1,000 higher than what you observe typically in background. So this is an enormous hydrocarbon mixing ratio. You don't see any of numbers like this here on the far right in Platteville in urban areas. Now this is an example from Warneke's paper, also came out just a few months ago, where they are driving a mobile lab around Colorado and Utah, and they can go relatively closely to well sites. Typical distances that you have in urban areas like in the Warneke Shale, and what you can see is that methane is typically highest close to the wellhead in separator and compressor areas. Methanol, which is used as an anticoagulant, an antifreeze, is close to its own tank, but sometimes also coming from the wellhead. Toluene is typically elevated close to the storage tanks, be that condensate or oil. So this example here is from a gas well that they passed by. It's not very much different from the oil well. And NO2 is typically elevated close to engines, of course, where you have combustion. Levels, toluene 40, 50 ppb high. So that's a very significant amount that would be giving you a benzene value also in the order 10 ppb. So this is not something that you want to be exposed to on a long-term basis, but that people in the Warneke Shale actually who live close to these wells may be exposed to on a regular basis. The second thing we have to deal with in the Eagle Ford Shale is the flaring. This is not happening to as large an extent in many other shale areas, but it's especially an issue in the Bakken Shale and the Eagle Ford. The problem with the flares is not that there are flares. The problem is they're uncontrolled, which means that the only rules that apply here are that the flare is operating and that the gas sent to it is metered. And the amount of air needed for the combustion is not controlled, which leads to typically smoking flares like at this one, which is a big picture from Karnes County, because it's very hard to maintain an optimal ratio between the fuel you send up the stack and the air diffusing towards the flame. So that's why these flares are also called diffusional flares, as opposed to controlled flares, which the chemical industry has to have, for example, in Houston, where not just the fuel is metered into the flame, but also the amount of oxygen. And thereby you can maintain an optimally burning flare, which you rarely encounter for a diffusional flare because it's strongly affected by how fast the fuel enters the stack, which is often not on, it's metered, but it's not controlled. And the second thing is that it's very hard to, in a natural setting, to keep the flow of oxygen to the flare. at the level that you need it. What we get from the flares is reactive hydrocarbons, especially ethylene and formaldehyde, and we get soot and associated PA agents from these. Let me orient you to some of the places that we got data from. Old Highway 90 sampler in the upper left. Calaveras Lake Monitor, won't go into that aside from mentioning it. Floresville. Two sites that are managed by Marathon. The Clute site by the coast, and a Hillcrest monitor in Corpus Christi. We've also used one other monitor in Corpus Christi. This is a map of July 7, 2014, updated from the Railroad Commission. San Antonio location, Wilson County, where the Floresville monitor is. The highest density is in Karnes County and neighboring counties. What we have done is we picked this area and said, let's look at air mass trajectories that go through this area after having passed the coastline and analyze them for their change in mixing ratio for ethane as a marker for the development of oil and gas in this area. There's typically 3 air mass trajectories going through this rectangle towards San Antonio. One that is exactly perpendicular, and 2 that take a longer time to traverse the shale area, either from southerly, southwesterly direction, but particularly for southeasterly direction. So keep in mind here, I'll come back to that later, when you go at an angle instead of the shortest way across the shale area, you would expect the concentration to be less because there has been less time to inject any fugitive compounds into that air mass. There's also a small gap in the exactly south of San Antonio in the shale, where you may have fewer emissions entering into the air mass. So what we find is that unconventional oil and gas has been increasing exponentially since 2010 in the area. The crosses here mark the 4th highest ozone for each year in San Antonio. And on the bottom you see a analysis of ethane data for all the years at 4 different locations. The red and green are the 2 coastal sites, and what you can see is that for a clean air mass origin out of the Gulf of Mexico, these levels have not changed very much at all. Variability has increased, such as in 2012, but the median has essentially not changed. So we're still getting more or less the same clean air from the Gulf of Mexico we always used to get, but the inland values have increased substantially. So the blue is the old highway monitor in San Antonio, and Floresville, for which we have only data since 2013 summer, is at the very end there, the yellow bar. So we have established through this graph that ethane concentrations in San Antonio, or in more generally downwind of the shale, have been increasing very substantially by about a factor of 3 since 2007.
Question?
When you look a little bit closer at Floresville data, there are several things that stand out. So this is the complete time series that we have analyzed here.
Gunnar, we had a question in the audience.
Yes.
Why are you measuring for ethane? Is it a marker? Why are
you measuring ethane as a marker?
Ethane does have various sources, but the main dominant source is oil and gas exploration, or more general natural gas exploration. You do have ethane coming from all oil and gas exploration, basically. There's essentially no other relevant ethane source that's around. So if you measure high concentrations of ethane in an area such as this, basically you're measuring oil and gas exploration. Does this answer the question?
Yeah, it did. Thank you.
Okay, so this is a complete time series, and two things I'd like to point out. We have a very low level at the bottom here, which is typically representative of background. So background is measured in Floresville every once in a while. We also have a very high variability. We get 50 ppb plus values on a regular basis. So in other words, all these individual spikes that you see are plumes that are coming by the Floresville monitor. And there is no particular season you see more of these plumes or fewer of these plumes, except for some individual periods, like at the end of the data set here, where you have a longer stretch without a large plume. You do see a very small seasonality in this. Ethane is typically higher in the winter, which has to do with the fact that we typically get lower boundary layers in the winter. And if we could zoom in to the background values, we would also see that the background is higher in winter, which has to do with the chemical lifetime of ethane in the atmosphere. The median here is already about 2 to 5 times the background. I will come back to this slide. When you look at the diurnal variation, you see what you would expect to observe, which is that typically during daytime you have much lower values because the ethane is emitted into a very deep planetary boundary layer, so it's mixed into a much larger air volume than it is mixed at night. The difference is typically on the order of 3 to 4. The day and nighttime average you see here is for particular hours. So when it says nighttime average, it's not for all nighttime hours.
Question?
But particularly for the nighttime hours where we looked into boundary layer depth.
Gunnar, we have another question from the audience.
Yes.
What is the difference in location between your instrument measuring the boundary layer and the instrument measuring the concentration, and is that important?
Yes, that would be important, but keep in mind, we did not do these measurements. All these measurements are from CCQ, and we do not have any boundary layer measurement instrument located anywhere close. So any boundary layer depth that you'll see in my talk or that you see anywhere else for this region are coming from models. There's no instrument that I'm aware of in this area that measures boundary layer depth. That doesn't mean that any boundary layer depth estimate is introducing a large error. This is, yes, it will introduce, of course, an error in any extrapolation. What we have found, though, is that presuming that these emissions are more or less steady throughout the day, so there's no period of the day where you have higher emissions than any other, the ratio in ethane between day and night matches relatively well with our estimates for boundary layer depth retrieved from an NCAR webpage. So what this means is that the boundary layer estimate from the NCAR webpage must be quite accurate, unless our assumption that the emissions are happening more or less equally distributed throughout the day were not correct.
Thank you.
So what we can do next is we estimated what we call the ethane enhancement at Floresville compared to the coast. So what you see here is typical background values of air blowing into Corpus Christi and typical values for the same time period measured in Floresville. And these are 24-hour averages here, and they give you an enhancement of 8.1 ppb for ethane. Now, because nighttime boundary layers are typically not as well estimated as daytime boundary layers, We have next only chosen daytime values for our extrapolation. So what we did was we chose a series of days throughout the year that have very clear air mass origins. And those air mass origins are the values that you see here as the different colors. Those are all what I call back trajectories that we have calculated using online program at NCAR called HighSplit. And you can see that they're all going through this rectangle, almost all going through this rectangle, I should say, and coming through Corpus Christi when they enter the coastline. We presume that we can treat the shale area as a line source, and there's a quite well-defined formula on how to estimate the emissions from a line source, which you see on top here. We need average wind speeds, we need the angle that the air mass trajectory is crossing the line source. We need to know boundary layer depth, which is that ZBL here. The air mass density throughout, and integrate that. This assumes that ethane is well mixed throughout this boundary layer, which is a reasonable assumption here because Floresville is significantly downwind of almost all the sources in the shale area. And last but not least, we have the NY here, which is our ethane enhancement factor. And in order to normalize this to all the sources, we divide by the thickness of the shale area, so to say, which will give us the value integrated over the shale area. Again, the presumption here is that the emissions over this area are uniform. I summarized some of the assumptions on the next slide here. Typical boundary layer depth for the time that we have selected is about 2,000 meters. That's a quite deep boundary layer. We have well-defined air origin. We have an air mass trajectory that's nearly perpendicular to the shale axis. Our ethane enhancement is about 4.6 ppb. Assumed uniform emissions. We also assume that the shale has a defined width, in this case 35 plus minus 5 kilometers. The next two assumptions are critical, namely that we can estimate methane emissions from the ethane enhancement. For this, we are currently assuming that the ethane-methane ratio is 8%, with a large error attached to that. If you carry this analysis through, you come up with a production loss in the 60 times 35 kilometer area of about 5%. The large error here is driven by the fact that we have two assumptions in there that are critical. One is the listed ethane to methane ratio. The other one is the amount of methane in the gas produced in the area. So at this point we're assuming that all the gas produced in the area integrates to give us a 90% methane content of the gas produced. And an additional, and 8% of that 90% is presumed to be ethane. So you can see that depending on which combination of these two values we use, that leaves room for other compounds of the natural gas, such as nitrogen, carbon dioxide, and higher hydrocarbons. This result of 5% is going to change. Other factor here, for comparison, I'm sorry, the recent paper by Schneiding estimated that the methane loss in the time period prior to our estimate was on order 9%. Okay, moving on to the hydrocarbon measurements other than ethane. What we've done is we used most of the data, which means all data where we had at least 30% of the time a measured value as opposed to a 0 or a non-applicable, and carried out what's called a factor analysis. It's a simple multivariate analysis that tries to identify the main factors that drive the abundance of various species. Whichever way you carry out this factor analysis, you always get two factors that are very well defined and various amount of a third, fourth, fifth, sixth factor. None of those are significant. So I listed one analysis here where I have a factor of 3. But let's look at the factor 1 and 2 first. Factor 1 is what we would call an oil and gas emissions factor. It is strongly driven by saturated hydrocarbons, and they stand out by having a very high number here. So if it were dominating the factor completely, you would get a loading, it is called, of 1 here. So you can see this is strongly driven by ethane, propane, and butane, but also pentane, isopentane. So all of these have higher than 0.9. They're very highly correlated with each other. The second factor is a typical combustion factor, which gives you alkenes, such as the ethylene and propylene, but also acetylene, which is typically used as a marker compound for gasoline combustion. So, in other words, tailpipe emissions. You can see that the beta species, for example, paramethoxylamine on the right-hand side here, and toluene, they score significantly on both of these factors. Loadings are typically not listed if they are below 0.2. I included a few here that are below 0.2 just to illustrate how close they are to 0.2 or how they compare to the larger loading. When you look at NOx, for example, top list on the left, it's mostly combustion, and it's not significantly loading on factor 1. Factor 3 has all values below 0.3 and typically accounts for less than 5% of variability in the data set, while factor 1 accounts for 50% variability and factor 2 accounts for 25% variability in this data set. We cannot identify a single third-pass factor that explains more than 5% of the data. When you try to explain, use these factors to explain individual compounds, you can see here that benzene is correlated with butane as one of the dominating factors of factor 1, and ethene is one of the dominating compounds of factor 2. And in sum of the two, you explain nearly 80% of the benzene variability. The highest benzene levels were measured when air came from the shale area. In comparison, different air quality concerned species, butadiene, cannot be explained by any emissions from the shale area. It's clearly dominated by the combustion factor, and we cannot explain quite as much of its abundance. When you plot the two common species, here I chose ethane and ethene, against wind direction for the Floresville site, you can make out a number of different things. So this is a what's called a box plot. The median value is the bar in the middle. The inner quartile range is the complete box. The whiskers are the 95% confidence level, and all individual data points that you see are flyers. Note that there are very few flyers whenever you have a west to north to about northeast wind direction. The large amount of flyers comes from southerly wind directions, easterly to westerly, about 40 degrees all the way to about 250 degrees or so. So these wind directions are dominated by air masses that have crossed the shale area. Then the obvious thing you see is that the medians of factor 1, which is the oil and gas factor, are elevated when the air was coming at angles over the shale area which maximize the time that the air mass spends in the area where we have oil and natural gas and oil extraction. In contrast, the highest values for the combustion factor are for the northwest wind directions where the city of Floresville is, so that's not too surprising. You can see slightly elevated values though also for ethane for the two wind directions that are highlighted for the ethane factors, namely easterlies and southwesterlies. Moving on to a reactivity comparison. So what is of importance for San Antonio may not be the direct emissions of these hydrocarbons, because many of them will be strongly diluted by the time that they arrive in San Antonio. What's much more important for San Antonio is, do these hydrocarbons represent significant atmospheric reactivity which will lead to ozone production during the transport into the San Antonio metropolitan area? So what I've plotted here is reactivity, which is more or less could be called the fuel to produce ozone. It's essentially the sum of the kinetic reaction factors for the individual VOCs times their abundance and then integrated over particular time periods. I have included methane and carbon monoxide, which typically represent a large amount of reactivity in the atmosphere. They dominate reactivity in the background atmosphere, typically do not dominate reactivity in polluted areas. Also included NO2 because it is measured at Floresville. I should mention here that the NO2, the NOx data at Floresville has a period that is biased. So I had to do a little bit of a correction on the NOx data, presuming that the bias in the data was caused by an offset in the instrument, which appears to be reasonable when looking at the data. I'm comparing reactivity to the Houston Ship Channel, measurements carried out by the NOAA group around Yost de Gauw, Jessica Gilman. These measurements were published in Journal Geophysical Research in 2009. Because the two data sets do not contain the exact same hydrocarbons, I have removed from the ship channel data set all the compounds that are not measured at Floresville. There's a few more compounds in there, so the comparison is not exactly a apples-to-apples comparison. Let me call it a apple species 1 to apple species 2 comparison here. For methane and carbon monoxide, which are not measured, you see that the values are all the same here. It's because I have presumed steady mixing ratios for these two compounds. I just show the northern hemisphere continental background for that. So what do we observe? First column is all data. Second column is when I only consider wind directions from the east to the south, which is one of those areas here that have the highest median. Third column, I only looked into summer values. What you can observe is that if I take all year-round values, I get a maximum for the reactivity of volatile organics. Third row here, 1.94, which is a little bit lower in the summer. Not too surprising for the fact that some of the hydrocarbons will react before they get to Floresville. So some of that has been lost. Compare that to the Houston Ship Channel, and you see that the total reactivity is actually not that much lower than in the area which is typically considered Texas' most polluted area. The similar conclusion can be made for NOx. which is on the order of 2/3 to 1/2 the activity we observed in the ship channel, which was very surprising to me because there is much less traffic, of course, in Floresville, particularly for the wind directions that I'm selecting here, because those wind directions are blowing the air produced from traffic in Floresville away. So I'm only looking at southeast, which is coming from the Shale area, and there's not a lot of traffic ahead of the Floresville monitor there. So in conclusion, we get something like 3 to 3.5 total reactivity, that's in per second, for the shale, for wind, for in-air masses from the shale area, compared to the Houston Ship Channel of 4.25. These are 24-hour values, so they are typically not the same during day and nighttime, but the same is true for the Houston Ship Channel here. So in that sense, these values are quite comparable. However, the composition, of course, is much different. In the Houston Ship Channel, most of the activity is driven by alkenes. That is the left bar here. Note that these are not absolute, but relative compositions I'm plotting here. Alkenes in Houston come from a variety of sources, but are mostly coming from the petrochemical industry, ethylene being one of the major compounds, not too surprising when you consider how many places produce polyethylene in the Houston Ship Channel. There's also a significant contribution of biogenics in Houston, because we have a significant amount of oak trees in the area. The part that I removed is the gray and blue part when I did the activity comparison. So I'm throwing a similar amount back into the mix here to show that there are oxygenates, of course, present also in the Eagle Ford area. We don't know exactly what they are. Significant contributors are most likely formaldehyde, acetaldehyde, methanol, and ethanol. Note also that if I select for summer data only, I get a significantly larger bar of biogenic compounds here. And that's for good reasons, because that biogenic bar is driven by isoprene, which is typically only emitted during summertime. Interestingly, this is in quite big contrast to data collected by UT, and the reason for that is that Floresville, the area around Floresville, has very few oak trees, while in most of the areas where UT took samples during last late spring and summer, you have a significant abundance of oak trees that contribute to isoprene in their measurements. So for my last part here, I'm coming back to this graph because I want to show you a case study that we have done on the biggest plume in here, which occurred in March 2014, and I've blown it up in this graph here. It shows two plumes that passed by the Floresville monitor between the 4th and the 7th of March. There's a number of features of these plumes that I want to highlight. On the top I plotted the lead alkane compounds, on the bottom the lead alkene compounds. You can clearly see that the plume was mostly composed of alkanes, but it also shows up in the alkenes on the bottom. The additional peak on 5th March in the ethene is interesting. What you have to know about this is that the wind shifted from south to northwest on the 5th of March. So this plume is clearly related to traffic in the city of Floresville. The wind then shifted back to southerlies on the 6th of March, and we got another plume passing by the Floresville monitor. The reason we think we know where this plume came from is that I looked through the complaints database and found a complaint that was filed on the 6th of March for a facility that's about 20 miles upwind west of Karnes City. And I pointed that out on one of the earlier slides, one of the Marathon facilities. The other important factor that was driving the size of these plumes, let me call it, in other words, the concentration here, was that this period was relatively cold and relatively clear sky. So we had likely a strong inversion layer that kept emitted hydrocarbons relatively close to the ground. At least for the first plume, if you look at the Calaveras Lake monitor data, you will see an effect of that plume that lasted about an hour after midnight, I believe, on the 5th of March. And you'll see it in the ozone and PM data. Now it turns out that we have activist footage from this same time period, taken with a FLIR camera. This is a screenshot of the FLIR footage taken on the 7th of March in the evening, and it shows a number of interesting features. For these features to come out, and I'm not sure how it shows on your screen, for these features to come out, I increased the contrast and brightness of this picture slightly. Notice that on the top of the picture, essentially you have a black sky. And on the bottom of the picture, you have a fog-like appearance. Now, what this means is that basically you must have had a relatively low boundary layer, as I mentioned before, which kept the pollutants close to the ground, and they kept accumulating around this site. The second feature you can take from this snapshot is that there's obviously a higher density of the identified hydrocarbons in this picture. One is coming from the flare, which is in the bottom middle. It's quite bright. The others are coming from obviously some other sources. Yeah? So the flare seems to be emitting a plume. There is another plume on the left of that, and there is some very diffuse plumes to the right associated with the tank battery. So this, together with two plume models that we ran on high split, which are shown on my last two slides here, confirmed to us that this very large emission from these facilities must have driven the observations at Floresville, which are marked here by the red star. So what you can see, I'm still not sure which monitor you're looking at. Do you see the picture, this animated GIF? Is it animated on your side?
Yes.
Yes.
Okay, good, that's making sure. So this plume is the first plume, and the defining feature of that plume is that after the start period right now, it is not going straight in one direction. Winds are very light, and they drift the plume only to a particular distance before it starts spreading. That's because the wind shifts to north and it goes away. This is corresponding nicely to the observed kind of fringe look of the plume at the Floresville monitor. Yeah? So what you can see is that it starts slowly, it comes up, there's a big dip in the middle, and then it goes away with some effect at the end of it before it completely gets cleaned out around noontime on the 5th of March. In contrast to that, the second plume is very well defined. It has sharp edges, and that corresponds very well to the analysis of the plume for that day, where the wind, as you can see now, shifted back south and created a quite well-defined plume which goes by the monitor, first impact, central impact, and then it goes all the way south, and Floresville monitor is no longer impacted. So these two events correspond very well and give us high confidence that for this particular case study we have identified the source of the plume.
Gunnar, there's a question from the audience.
Yes.
Gunnar, can you tell us the significance of that blue area, just something that us lay people can understand? The concentration in the blue that's sweeping. What if you were,
Okay, yeah,
if you
so
were
the question
standing
is
there
about
compared to
the
automobile?
concentration levels in the plume. Keep in mind that we have no idea what was actually emitted at the site, so this is a purely qualitative analysis of the plume. What is useful, though, is the color codes identify the order of magnitude difference between what you have in the plume. Yeah? So you can see that the yellow is the highest concentration, then the dark blue, the green, and the cyan. What this means is that if you presume that for the second plume, that Floresville, the highest concentrations at Floresville were in the green, then you would have had at least 2 orders of magnitude higher concentration at the release site. So a 100 ppb ethane would have translated into a 10 ppm ethane at the site. If you translate that to a compound of interest, such as benzene here, benzene at Floresville in this plume was 1 ppb. So it would have been 100 ppb, potentially up to 1,000 ppb at the release site. Keep in mind that these are large-scale averages because this model has a resolution that is not better than, let me think, was it 4 kilometers or 10 kilometers? Don't nail me down on this one, I have to double check that. What I'm trying to say by that is the concentrations you see here are averaged over a much larger area. So if you are close to the release source, they may have been another order of 1 or 2 orders of magnitude higher than suggested by this simple analysis. Does that help?
Yeah.
Okay, so very quick, some conclusions. I think what you're dealing with is very high hydrocarbon pollution from the shale area. We have an order of 10 to 100, factor of 10 to 100 higher levels than background, and that's downwind. So if you live close to one of these sources, you may experience even higher concentrations at times. So specifically, when we have a situation like in this case study where you have very low boundary layers which lead to a high accumulation of hydrocarbons close to the ground. I don't think these are upset emissions. This particular case study, there's nothing in the upset database, so we have no idea if there was anything specific happening or if this was actually business as usual. It looks more like the latter. You do have very high reactivity. It's of similar magnitude than in Houston, which is considered one of the most polluted areas in Texas. So what I can conclude from that is that you will definitely have effects on regional ozone. The question is how high. You do have regular pollution plumes, as I tried to convey through the timeline of the ethane data. It's not just every once in a while that ethane is high, it's basically on a regular basis all the time. The emissions must be widespread, otherwise you wouldn't see this at the Floresville monitor all the time. We do have regular inversions, unlike in an urban area where we have a heat island effect. This is the countryside, so you get inversions there a lot, also because humidity is lower than in in East Texas. And we do have now a quite large database of well-documented health and nuisance effects. So this is potentially of concern, maybe not for you, but definitely for people who live close or will be living close.